Hello and welcome. What did the buffalo say when his son left for college? Bye, son. In this video, we're going to finish up some loose ends by looking at two theorems, Rolle's theorem and the mean value theorem. These theorems are primarily theoretical tools used for proving things in calculus, but they'll also be good for strengthening our understanding of the derivative. So let's get started. Let's first look at the picture on the right side, where we have this upside down parabola, and then we have this line right here at y equals 1. So we'll try to get a visual understanding of what Rolle's theorem is saying. So Rolle's theorem is basically saying that if there's if there's a place where you have the same function value, so right here at x equals 1 and at x equals 5, the function value is the same. Let's actually label those. We're going to call that x equals 1, we'll call that a. And then x equals 5, we'll call that b. So f of a is 1, f of b is also 1. So if that's the case, and if your function is continuous on that closed interval from a to b, so from 1 to 5, and differentiable on the open interval from a to b, from 1 to 5, then there has to be at least some number c in between a and b, so some number inside of your interval, at which the derivative of your function is equal to 0. In other words, where you have a horizontal tangent line. Now if you track along the function, well, here the tangent line looks like it's a little positively sloped, a little bit less positively sloped. Right up here at the top, we're going to get a tangent line that has slope 0. So that's going to be the place where the first derivative is equal to 0. Right there. So where that happens, the x value where that happens, is the c that's being talked about right here. So there's got to be some place where the slope of the tangent line is equal to 0. Now that kind of makes sense. If you think about the function as being like an altitude of an airplane, right? And so this is at t equals 1 here, the plane starts at an altitude of 1 mile up in the air. Then the airplane is climbing up, and so it's going up, and at t equals something 1.5, the altitude is now 2 miles in the air. And now it's still going to climb up, so at t equals 2, it's about 2.7 miles in the air. And then at t equals 3, it's 3 miles up into the air, and then it starts to nosedive. No, it starts to fall in altitude. So at t equals 4, it's back down to like right around, 2.2 or something, and so on. Until at the end, at t equals 5, you're back to the same altitude of 1. Now if you imagine that airplane going from t equals 1 to t equals 5, starting off at an altitude of 1 and ending at an altitude of 1 mile, then at some point in that time interval, the plane's got to turn around, right? There's got to be like a peak of the altitude, because it can't just keep going up. It's got to turn around to get back down to an altitude of 1. So intuitively, this makes sense. If you have a dot right here with an altitude of 1, and a dot right here sometime later with an altitude of 1, at some point from the start time to the end time, the plane's got to turn around. And when it turns around, that's where the slope of the tangent line will be 0. So turning over to the formal statement of Rolle's theorem, it's saying that suppose that 1, f of x is continuous on a closed interval from a to b. That way you can't just suddenly jump up or down. You have to have the function continuous, like an airplane would be. It's got a continuous altitude. It doesn't jump around or anything like that. It's not like the plane goes through wormholes or anything. Then for number 2, f of x is differentiable on the open interval from a to b. So it doesn't technically have to be differentiable at the endpoints, but as long as inside of our interval it's differentiable, that's okay. And then 3, f of a equals f of b. This is just saying what we said at the very beginning, where the altitudes are the same. So f of a is equal to f of b. In this case, f of a and f of b are both equal to 1 in the picture. then if all these things are true, then Rolle's theorem says that there has to be at least one number c in our interval from a to b. So there has to be some time from between the start time to the end time at which the slope of the tangent line, so f prime of c, is equal to 0. So there has to be a time where we're turning the airplane around, in other words. All right, well, let's see how in example 1 we're going to use Rolle's theorem to help us out. Oh, actually, in example 2 we're going to see where Rolle's theorem can help us out. Example 1, we're just going to get to know Rolle's theorem. It just says verify that this function satisfies the 3 hypotheses of Rolle's theorem on the interval from 0 to 3. So there's our interval, there's our a and b. Then find all numbers c that satisfy the conclusion of Rolle's theorem. So we're going to take this in 2 parts. First, just verify that all the 3 hypotheses are satisfied. So I'll keep those hypotheses up there. Well, one thing we're going to need is to know the derivative of our function. That's going to be especially for part 2, the second part where we're trying to find the number c. So let's get that out of the way. We have 3x x squared minus 2x minus 6. Now we're going to verify the hypotheses. Hypotheses are like the conditions of Rolle's theorem. So 1, we're going to say that f is continuous on the closed interval from 0 to 3, since f is a polynomial. And is continuous everywhere, including the interval from 0 to 3. 2, f is differentiable on the open interval from 0 to 3. Again, since it's a polynomial, I'm just using those quotes to say the same thing. 3, f of a equals f of b. So 3, f of a is 0, and then is equal to f of b, which b is 3. A little better. Both of these, if you look at f of 0 or f of 3, you're going to get 2. And you can double check that. If you plug in 0, well, it's pretty clear it's 2 because all these terms would become 0 and you just get 2. If you plug in 3, you'll get 27 minus 9 minus 18 plus 2, and that also gives you 2. You can also peek over at the picture and you've got f of 0 equals 2 and f of 3 equals 2 as well. But we're not going to be given the picture in all these cases. Okay, so note at this point that what Rolle's theorem would say. All those 3 hypotheses or conditions have been met, and so Rolle's theorem would say that there has to be some value c in the interval from 0 to 3 at which the derivative is equal to 0. So note that Rolle's theorem now says there must be a c in the interval from 0 to 3, it rhymes, at which f prime of c is equal to 0. That's just a little note, because then in the next part we're going to find all the numbers of c that satisfy the conclusion of Rolle's theorem, which we just wrote out. This is the conclusion of Rolle's theorem, that there has to be a c in the interval from 0 to 3 at which f prime of c is equal to 0. So we're going to figure out the values of c that satisfy this conclusion of f prime of c equals 0. Let's find c. Where f prime of c is equal to 0. All right, well, f prime, whoops, lost it here. So f prime of x is 3x squared, so that's 3c squared, minus 2x, that's minus 2c, equals 0. There's a quadratic we can solve. Doesn't quite factor though. All right, we're gonna have to break out the quadratic formula. Here goes. negative b plus or minus the square root of b squared minus 4ac over 2a. Okay. Now, if simplifying, we've got 2 plus or minus the square root of, it's going to be 4 plus 12 times 6, that's 72 over 6. So we've got 2 plus or minus the square root of 76 over 6. Let's see, does 4 go into 76? Yes, 4 goes into 76. So we're going to have the square root of 4, which is 2, and then 4 goes into 76, 19 times. Thinking about the division, over 6. Okay, got some more simplification to do. We can divide the whole top and the whole bottom by 2. I'm going to write it out there. Divide whole top and whole bottom by 2. Just to remember that we're not canceling off the 2 factor of 2 with the first terms here. We have to divide the whole top by 2. That means dividing this by 2 and this square root part by 2. Or the part that has the square root attached. So here we're going to have 1 plus or minus the square... Whoops, I'm writing in red. 1 plus or minus the square root of 19 over 3. And you know what? I'm going to write c equals that at this point. There. So there are two c values that could work here. One is 1 plus the square root of 19 over 3, and one is 1 minus the square root of 19 over 3. The only thing is that one of those doesn't really belong. So let's do a little note. One minus the square root of 19 over 3 is not in our interval from 0 to 3. We're saying this is a c value that's inside of our interval from 0 to 3. So let's go ahead and erase that negative right there. So we just have 1 plus the square root of 19 over 3. There we go. Okay, so that would be the c value that satisfies the conclusion of Rolle's theorem. Just to tie this to the picture that's off to the right, here's our function. We mentioned that f of 0 is 2 and f of 3 is 2, so same altitude. So if you're going to draw a curve from that dot to that dot, somewhere along the line you have to turn around. Right, here's the airplane, it's dipping down, it crashes into the x-axis. This is probably not a good example for altitudes. Oh, I know, they're in Death Valley, so you actually have negative feet. Maybe not negative 6 miles anymore, but so this airplane, or going down a big tunnel or something. So this is a airplane going down, down, and down, and at some point it's got to turn around for it to come back up to the same altitude of 2 miles. And that point is 1 plus the square root of 19 over 3. Square root of 19 is about 4, so 1 plus 4 is like 3. It's a little bit bigger than 3, bigger than as 5. It's a little bit bigger than 5. 5 divided by 3, that's like 1 and 2/3. Yeah, that's about right. Right around here. It's a little bit bigger than 1 2/3. That's where you get the horizontal tangent line. Right there. At 1 plus the square root of 19 over 3. All right. Thanks so much for watching this video, and see you in the next one.